Next up, we're going to do an example using spherical coordinates. And I started doing this example and realized I couldn't draw a sphere. So I've started over and pasted in a picture of sphere for us to work with. And the problem is to integrate f equal to x squared plus y squared plus z squared over the top half of a sphere with radius 2. And to be clear about what I mean by top, I'm saying the part where z has to be positive and x and y can take on any values. And it's that piece that's in this picture right here, where I've got a sphere that's been cut in half, and it all sits sort of like in the xy plane and higher. So we don't go down below z equals 0. We cut a sphere centered at the origin in half using the xy plane. And it has radius 2. And so we know this is going to be a problem that's easy for spherical coordinates because it involves a sphere. Also, a good tip is that we see terms like x squared plus y squared plus z squared. That can tell you you're looking at something kind of spherical. And so we need to find our bounds of integration. And so we're going to need those for theta, phi, and rho. Okay, so I'm going to go with theta first because it's old to us. When I look at the sphere, I can see that I go all the way around, starting from the x-axis, and I reach back to the x-axis. So my theta is, again, just 0 to 2 pi. And then rho is new to us, but closer to something we knew before than phi. So I'm going to do that one next. This picture looks hollow, but it is supposed to be the whole shaded in sphere. So the shortest distance we ever are to the origin is 0. We reach all the way to the center of the sphere. And then the furthest we go out is just the radius of the sphere, rho, which is 2 everywhere. And then phi is the one that's tricky. Phi is going to start at the positive z-axis and then spin down. So we're touching the positive z-axis. So just like when we touch the positive x-axis, we know theta starts at 0. So since we do have shape right here, we know that phi starts at 0. And then the furthest down it ever goes is reaching down to the xy plane. So it's gone down 90 degrees, or an angle of pi over 2. I know that that can be hard to get the hang of looking for, but just a good rule of thumb would be to define theta first so that you know you're not overthinking things, and then think about phi after that, kind of because if one angle's out of the way, then it's easier to focus on the other, and theta is the one you already know, so it's usually easier to do first. A warning I will give is that there might be a temptation to like say, okay, well, I touched the z-axis, but I also go back from it. So I could do minus pi over 2 to plus pi over 2 for phi. But if you do that, then defining theta is hard because kind of you would think, okay, theta goes here, but theta also goes here. And what you would do is kind of like, you would define too much shape. You've already covered this back half of the sphere when you spin theta all the way around. So kind of the way you can think about it. Oops, I gotta erase this. Is here's a little like quarter circle slice of the sphere that's created by my phi angle, right? And then if I like could imagine that I have like a paint tool or something, and I hold this shape in place and then I drag it all the way around with my theta, I've created the whole sphere. So that little paint wedge would trace out all these different quarters all the way around from 0 to 2 pi. If I define that paint wedge slice as like a half circle, Then when I start to spin theta around, I would only go this far and then sort of imagine you've rotated it through and covered the entire sphere. But you won't remember to only do that half of theta. You'll think it goes all the way around, so I do the full theta. So that's why it's important to always think about starting phi from here and going down, or else you'll double over it with your theta if you're not careful. A lot of that might not have made sense. I promise it'll make sense as you do these practice problems and make those mistakes for yourself and just learn what works and what doesn't in these systems. So my order of integration doesn't matter because everything's constant. So I'm going to do my angles second and my phi first. And then my f was x squared plus y squared plus z squared. And I remember that the substitution for that is that x squared plus y squared plus z squared is just rho squared. In my dv, my dz, dy, dx, I'm doing an order of integration d rho, d phi, d theta. And I have to remember to replace this part out front with rho squared sine phi. Okay. So that's 0 to 2 pi, 0 to pi over 2, 0 to 2, rho to the fourth, sine phi, d rho, d phi, d theta. And so let's go ahead and work through that. Again, just giving us practice with these triple iterated integrals. I know that they're hard. I know that it's easy to forget the order to do things in. So we're just going to go ahead and practice. So we look at the innermost integral first. That's with respect to phi. So my outer integrals stayed the same, and my sine phi may as well be a constant. And when I integrate rho to the fourth with respect to rho, I end up with a rho to the fifth term times 1 over 5. And that ends up being 2 to the 5th over 5 minus 0. So 2 to the 5th minus 0 over 5, just 2 to the 5th over 5. So I guess that's 32. 2, 4, 5, yep, 16, 32. Cool. So that's 32 over 5, integral from 0 to 2 pi, 0 to pi over 2, sine phi, d theta. And so now we look at the next innermost integral. That's with respect to phi. So when I integrate sine phi with respect to phi, my outer integral stays the same. And then sine phi integrated gives me cosine phi with a negative, because cosine is the one that changes signs. Evaluated from, I never wrote that 0 to 2 there. Evaluated from 0 to pi over 2. And then my d theta is still right there. So that's going to give me minus cosine pi over 2 minus cosine, so plus cosine 0. D theta. Let's see. So cosine 0 is 1. Cosine pi over 2 is 0. So that just becomes 1. I'll actually leave that there. It's fine. So this is just 32 over 5, integral from 0 to 2 pi d theta. And I'm completing this last integral with respect to theta. It just becomes theta. 32 over 5 times theta evaluated from 0 to 2 pi. So that becomes 32 over 5 times 2 pi 64 pi over 5 would be my answer. And that's how we do spherical integration. So once it's all set up, just this approach to triple integrals isn't exactly new, but I think it's nice to be kind of slow and deliberate and practice a lot of these. So